Now let's take a look at the SoftBodyEdges settings. The pull value controls how much a vertex resists being pulled away from the vertices around it. A low value will make it really stretchy, and a high value will make it really stiff. If you're into physics, this is called the tensile strength. The push value, on the other hand, is how elastic or inelastic the springs connecting the vertices are, which is how much it will resist being squished together. The higher the value, the more it will resist compression. The damping was a little bit easier to see on a subdivided cube instead of an icosphere, so I'm using that for my example. A higher damping value will add more friction between vertices, which makes it jiggle less and come to rest a bit faster. Plastic is how much the deformations are permanent. A low value means the soft body will try to get back to its original shape, and a high value means it keeps all of the dents and dings it gets throughout the simulation. So in the last video, I explained how each vertex is connected to the ones next to it, but the bending value actually extends the reach of that chain. It's a little bit easier to see what I'm talking about in edit mode, so I'm just going to select our icosphere and go into edit mode really quick. So let's say that this vertex right here is the original vertex, and if we press Ctrl+, it'll expand the selection, and this is what it would connect to by default. But by increasing the bending, say we increase it by 1, it's going to add 1 more to that chain, and so it's going to be connected to a lot more vertices. And if we increase it even more, say 2, 3, 4, 5, 6, 7, 8, 9, 10, it'll reach all of the other vertices, meaning that that one vertex is going to be connected to every other vertex in our object. But if we had, say, a lot more vertices, let's just hit this, select everything with A, W, and subdivide. Let's do that one more time. Select a vertex again, and let's say that that is the original connection, and if we increase it by 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it'll be connected to all of those vertices. So you can see that the more vertices we have, the less stable it's going to be, but by increasing the bending, you're going to increase the structural integrity of this object and keep it a little bit more stiff. So if you have a lot of vertices connected to each other, it's definitely going to slow down the simulation because it's going to have to connect to every single one of these instead of just the ones around it. So the higher you set this, the slower it's going to be, but also the more stable and solid your object is going to appear. Stiff quads makes a new diagonal spring across quad faces so they don't collapse in on themselves, and the shear value is just how stiff those new springs are. A high aerodynamics factor makes it so the vertices with only a few connecting edges fall a bit faster than those with a lot of connecting edges. Simple and lift force are the two ways Blender can use to calculate this, but they pretty much do the same thing, although lift force is a little bit more physically accurate and sometimes looks a little bit more interesting. Lastly, you can make edges and faces collide as well, so that the things that vertices don't hit will still collide. So there you have it. You should be able to set up your own soft body simulation inside of Blender. There's a couple things that I didn't cover, namely the soft body cache, which we've talked about caches in the previous videos. This is exactly like the cloth cache. I need to go over it again. There's also the field weights, which are the same for every other type of physics. There's also a soft body solver, which has a few extra advanced options. One thing to note though with this is the step size, which we've looked at step size for rigid bodies and cloth and everything like that. However, in this case it's a little bit different because there's a minimum and a maximum, and it blends between the two based on how fast the object is going, which is a really clever way to minimize memory when we don't need it, and to keep things really precise when things are going fast and are more likely to intersect with each other. So that's all for soft bodies. I will see you in the next section.